Okay, in this video we are going to evaluate a scalar line integral over two different paths. And so the first one's going to be a straight line and the second one's going to be a parabolic curve. So let's take a look at it. We're going to evaluate the integral along c of x ds. And first it's the line segment x is equal to t, y is equal to 2t. We're going to start at 0, 0, and we're going to end at 2, 4. So let's think about what a line integral is in general. So hopefully this is something that's in your brain at this point. So we write that down. And then in practice, to actually evaluate these, what we do is we parameterize everything and turn it into basically a single variable integral. So that's what we're going to try to do. So it's going to become the integral from a to b, so those are t values, f of r of t, and then ds is the magnitude of r prime of t dt. So to evaluate these, really the first key thing is to figure out what r of t is. So if we can do that, we're pretty much set. So in this problem, r of t is kind of given to you, right? Because we need some parameterization for x and some for y, but if you look at the givens, we know that x is equal to t, so that's done. And we know that y is equal to 2t, so that's also done. We need to know the t values, so the boundaries, where you're going to start the path and where you're going to stop the path. 0, 0, if you look at what x is equal to and y is equal to, that definitely starts at t equals 0. So 0. And then we go until x is equal to 2, and if x is equal to t, then t must stop at 2. Okay, so we have almost everything that we need. I'm going to start writing my line integral. So it's going to be the integral from 0 to 2. And then we need to parameterize this function. So the function f of xy in this case is actually just x. So right there, and then I know that x is equal to t because that was given to me. So I'm just going to write t. And that's the entire function. We're done. We move on to the ds portion. So to figure that out, we actually need to know what r prime is, which we can just find component by component. So the derivative of t is 1, the derivative of 2t is 2. So we get this. I need to know the magnitude of that vector. So square root of 1 squared plus 2 squared is square root of 5. And now everything is a function of t, so dt. And this now is like a Calc 1 kind of basic integral, so let's just evaluate. I'm going to pull out the radical 5. I'm going to reverse the power rule, so plus 1 times reciprocal. And then I'm going to evaluate from 0 to 2. And when you plug in 2, you get something. When you plug in 0, you get nothing. So it's going to be 1/2 times 4. And then that's just going to give me 2 root 5. All right, so this particular scalar line integral is 2 root 5. Let's do, it's going to be the same function, so the same f of xy, but a different path. So let's see what happens here. So this time, our path is x equals t, y equals t squared, and there we're going to go from 0, 0 to 2, 4. So same starting and ending points, same function that we're working with, but let's see if the line integrals are the same. So again, we want to parameterize everything, basically turned into a function of t so that we can deal with that. I think people are usually surprised by like how simple these end up, but you know, take it and run with it. So we'll find r of t, which again is basically given to us in this problem. So x is t, y is t squared. We need to figure out the t bounds, but again, x is just equal to t, so you can just look at the x values. So we're going to start at 0, and we're going to end at 2. All right, let's see. So writing this, it's going to be from 0 to 2. And then we need to parameterize this. Again, x is just equal to t. So we can just rewrite this as t. And then we need to figure out ds. So at this point, it looks very similar. So you might be thinking we're going to get the same answer. The key here is that ds is a little bit different. So let's find r prime. So component by component, we get the derivative of t is 1, the derivative of t squared is 2t, and that's where the big difference comes in. So I need the norm of this thing, or the magnitude, so that's going to be the square root of 1 squared plus 2t squared is 4t squared. So that's going to be the magnitude of r prime, and that's a big difference. Last time it was a constant. So let's plug this in. Now everything is a function of t. Okay, so I need to evaluate this integral, and it's still just going to be, well, it's kind of like a chain rule problem. So if you want, you can write down u is equal to 1 plus 4t squared and integrate from there. I tend to just look at them and think, so if u is 1 plus 4t squared, then du would be 8t dt, so there should have been an 8. So I'm going to write 1/8 to balance that out. And then it would be u to the 1/2, so plus 1 would be to the 3/2, so I need a 2/3, and then the whole quantity, and then to the 3/2. So if you don't like that, just, do the u substitution, which might be easier. It's just a lot more writing. Okay, so when we plug in 2, we're going to get something. In this case, when we plug in 0, we also get something. So watch out for that. That's a really common mistake. So that simplifies to 1/12. Plugging in 2, I get 1 plus 4 times 4, so 17 to the 3/2. And then when I plug in 0, I end up with 1 to the 3/2, which is just 1. So minus 1, close it. It's not going to get better than that, so I'm going to leave it. So you see we did the same line integral, except took different paths. If you think of a scalar line integral as kind of giving you the like the surface area of a wall or a fence, where f of xy is the ceiling, I guess, that you're going up to, then it kind of makes sense that if you take different paths, you're going to get a different sized wall. So I'm not surprised by this result, but I hope you found this helpful, and good luck.